Hey everybody, welcome to Innovator Café. Today we're joined by Ashitosh Swarup, Ash, an inventor, an entrepreneur, and a very colorful and interesting journey in his career and his life, and I can't wait to hear more about it. Ash, welcome to the show.
Thank you. I'm happy to be here.
Yeah. So Ash, let's talk. Let's go back to the beginnings. Where you're from and where this all started.
Okay, of course. So let's go back right to the beginning. I was born in India, but then for a few years, my family moved to Nigeria. Somewhere down the line, I developed an interest in aircraft and planes. And as a kid, I wanted to actually become a pilot when I grew up.
No kidding.
Yeah, I did. And it was not without its hiccups. I watched the airport series, with the airplane disasters, and that put me off a little bit. But somehow I kept going on. I'm like, yeah, I want to be a pilot. But then these guys came along, and back in the day, if you have glasses, you can become a pilot.
Wow.
Yeah, and then. Yeah, I wanted to fly like fighter jets and stuff. You're a kid, you like the fantasy of flying fast through the air and
Sure.
kinds of
Sure.
stuff. Yeah, so I kept that fantasy going for a little bit, that idea, maybe I'll become a pilot. But as I grew up, I did start getting very interested in technology, the process of engineering, the process of building. And I figured if I can't fly these planes, maybe I could get into the business of making them.
Incredible.
So, so that's when I decided maybe the path of engineering would be a good way to go, right? And then, so in India, I applied to engineering school. I got my bachelor's in electrical engineering, and I decided I did want to go further and study the advanced technologies that would go into the aerospace engineering concept.
Right. What was your first school in India?
So that would be the University of Bombay, the University of Mumbai now. Back in the day, they called it Bombay. Yeah, so
Right.
that was my engineering school. It was a regular 4-year degree, and one of my favorite courses was actually control theory, control systems, because that's when I realized that a lot of the control theory control systems are actually applicable to flight control systems. So you study all these stability principles where you have your system. So whether it's your car or it's your airplane, you want to stabilize it. And that started the various mathematical concepts of stability, observability, and things like that started to fascinate me. So I applied to grad school in the US. Fortunately, I did have a green card back in the day through my mom. My mom's family is here, so we were able to do that, and so that transition was relatively straightforward. I came in and I tried a few schools. I initially went to Utah State University, Logan, and I found out they had a space dynamics lab there in collaboration with NASA, and only to realize that the professor who was working there had left to go work full time at NASA. So I came back to California, spent a couple of months with relatives, and then went to the University of Florida in Gainesville. I stayed there a semester, only to find out that the professor who was running the avionics lab had moved back to Italy.
A lot of movement in the space.
Yes. So during that semester, I applied to UCLA. I had a professor there. I came back to California, settled here, been here ever since. I got my PhD from UCLA. And while I was wrapping up, my advisor, he had started a startup company. And they were doing these government grants, SBIRs and STTRs. I worked with him on that was a fascinating experience. I worked with him as I was finishing up, and after I graduated, I went and worked there full time. That's when I got my real hands-on experience. We did stuff again, the vehicle control, flight control. I did stuff working on missile guidance. That was actually that was my first patent, my PhD dissertation, the core algorithm. They took that and applied that to missile guidance algorithm.
We'll talk about that. I'd
Yeah.
like to hear more about that.
Yeah. And then that's when I did some stuff on hypersonic cruise vehicles. And excuse me. And one fine day, one of the engineers, he was also the chief operations officer. He comes in, he puts a digital signal processing board on my desk and said, "Build us a GPS backend." I said, "I've never worked with this before." He says, "You will now." And that's how I got started in the embedded processing, the boards. I added FPGAs, and eventually we were able to build a whole GPS system back end. By the time I left, it was actually, we were pulling in 6 satellites in real time and tracking them across the sky. I eventually got my own grant and I spun off. I started my own company, and that's when the chaos theory applications started. I did some work. There was another government grant that supported me for a few years.
Talk about chaos theory. What is that for our listeners?
So, very, very fascinating area of study. When we say chaos, we think all craziness and lack of structure and things that are out of control, but it's actually quite the contrary. So chaotic systems, they are random looking, but they're not random. So they're governed by very nonlinear equations. And when you see the output of this equation, of each of these equations, it looks like it doesn't make sense. But yet, when you go back and use the same equation and the same initial condition, you get the exact same waveform. So if something is totally random, it's not repeatable. Yet chaos is random looking, but very repeatable. So when you can control the amount of randomness at one end, if you have knowledge of the system, but another person does not have knowledge of the system, and if you send information between 2 people who know the system, that's a good way to send secure and encrypted communication. So for a third-party observer, it looks like you're communicating with gibberish or noise. It just looks like a noise transmission. But for people who are aware of the system and its intricacies and the secret keys, it makes perfect sense.
That's fascinating. It's fascinating. Well, tell me how that differs from typical key theory in encryption.
So encryption generally is used for digital data. So you have your ones and zeros. And the beauty is encryption can be used in conjunction with chaos theory. While chaos can also be used to create encryption keys, the beauty of chaos theory and the chaotic waveforms is that you can introduce this kind of security and randomness at the waveform level, this at the base level where you're sending your signals out. You can
So when they're looking for a digital signal, they're really seeing this crazy random signal coming in.
Yes, and the digital signal is embedded within it with the encryption keys. So not only do you have your encryption, you also have your waveform randomization. So for anybody who attempts this to decipher the signal, it's just so difficult.
It starts at the analog level first, right?
Exactly.
You have to figure that out first.
Yes. And with good signal processing, you can actually make these signals so that they run below the noise floor. So the power level is actually below the noise floor. Like the GPS.
What does that mean?
Right. So around us, we have all kinds of electronic noise. And there's a certain baseline level, which is the noise floor. There are signals, this class of signals like spread spectrum signals, chaotic signals are one of them. GPS signals are another class of such signals. So when the GPS signals come in from the satellites, they're so weak that they're actually below the noise floor. You can't see them directly on a spectrum analyzer. You have to actually extract them and then pull the signal out from below the noise floor. So it's kind of hidden below the noise floor. You cannot see it. Same thing with chaotic signals. You can actually bury them under the noise floor where they're not visible. All you'll see is just the noise. And then when you, at the receiver, you perform your signal processing, since you know that you have knowledge of the system and you can actually extract the signal from the noise floor.
So how is it possible to hack such a signal?
To
hack such a signal? I mean, where would you begin to try to hack or try to read
Oh,
a signal without the keys?
It's really difficult. It's really difficult. You have to use advanced signal processing techniques. You have to be aware that the signal is there in the first place. Or you have to use a wide range of scanning techniques and scan each frequency bandwidth and perform all kinds of signal processing to try to pull the signal out. It's extremely difficult to hack them.
It sounds like a lot of trial and error. I mean,
Yes,
you're searching for the signal.
Yes, they call it a brute force technique in the field of cryptography. So sometimes if you're not aware, you may have to brute force your way to see if these signals are even present.
Sounds like magic. Fascinating. Fascinating.
Well, yeah, it's really quite intriguing. It's really interesting. It's been fascinating. I've been working in this area since 2010, and the more I look into it, the more I learn, and I feel we've just scratched the surface. There's so much structure and intricacy here that there's a lot waiting to be learned.
How did you first apply it?
So I applied it for the first time as a part of the research grant from the U.S. Army. They had a solicitation where they wanted to develop a wireless communication systems using these classes of waveforms for satellite communication. So in the battlefield, where you have your soldiers communicating wirelessly, they wanted some kind of encrypted, low visibility, hard to hack waveform that they could use for the communications throughout. So that was my first experience with this class of waveforms. Now, I had already done work on the GPS system at my previous job, at my previous place. So it made it easier to understand the structure of the signal and apply some of those spread spectrum communication algorithms and techniques to modifying those systems, the existing technology, into incorporating these chaotic waveforms. The main challenge was a lot of the previous digital communication was just ones and zeros, binary phase shift keying. Right. This one, a chaotic signal, has a full dynamic range. It's a floating point value. So you have to adapt the system using multi-bit A to D converters and D to A converters. But yeah, that was the progression, and that was the first time I got involved.
Very interesting. Tell us about the grant and how you got it. You know, a lot of people apply for grants. It's kind of an evasive system. How did you get the grant for your technology?
So what happened was, it's actually a kind of a sad story. The chief operations officer who gave me that signal processing board, he passed.
Huh.
Yeah, it was sad. We worked well together. He was the analog guy and I was the digital guy. So he was developing the front end, I was developing the back end. We also had a CEO. He was also my advisor student. He decided to leave and go work at JPL. So there were a lot of structural changes. And at that time I was living in Burbank, and they decided to move all the way to El Segundo. I was not sure I wanted to make that lifestyle change. So I started exploring options. And one of the things I found was this grant. You know, the company I was working for, my advisor's company, they were doing these, you know, that was their job. They used to apply for these grants and win these grants. And that was the revenue that they were a research firm, and they were working off of, or sustaining themselves off of these SPR grants. So I had experience writing a few of these, and I had won a couple of them. So I decided, let's take a chance and let's write one of these for ourselves. And So it was interesting. Back then I was married and my wife was at Cal State LA. So I remember going to the library and pulling books on satellite communication and spread spectrum communication and seeing how it would apply all these concepts and modify them to adapt this new class of waveforms.
Mm-hmm.
I wrote the proposal, and apparently the technical point of contact liked what he saw and decided to award us the grant. That was a big moment in my life. I was really
Big breakthrough.
Yeah, big breakthrough. So,
Mm-hmm.
I wanted to stay in Burbank, and I didn't want to move all. It would have been a hike to El Segundo every morning from Burbank
Mm-hmm.
down to 405. So that
Yeah.
was really awesome.
Right. Excellent. Excellent. Well, talk about some other applications of this technology.
There's very broad applications. So anywhere you can use waveforms,
Mm-hmm.
you can use this system. Satellite communications, any kind of wireless communication systems. We have a patent right now where we're using this for a wireless medical transducers. So we have these transducers all over the patient's body, and the nice thing about chaotic waveforms is that if you change the initial condition on a chaos system, even a little bit, you get a totally different waveform. So when you have all these sensors on a body, you initialize each system with a slightly different initial condition, and each transducer emits a different waveform. So you have your node ID problem in this mesh network resolved at the waveform level. You don't have to go down into protocol to see which node is transmitting which waveform.
Right. So you have 100 patients on the same floor.
Correct.
Each of them have their own unique sensors, and signals are flying everywhere. How do you sort them out?
Exactly. So these waveforms give us a way to do that. Radar systems, you can use these waveforms. Again, these are the noise-like structure. You can do all kinds of things with them where the adversary may not know that you're even tracking them or using these waveforms.
Mm-hmm.
Things like that. We've even explored optical communication using these kinds of waveforms.
How does that work?
So basically, you have a laser beam,
Mm-hmm.
and you modulate the light of that laser beam chaotically as you send that to the optical fiber.
Got it. So it looks like optical noise going through.
Exactly. So that's another way you can do that.
Is it the same level of security as an electrical signal?
Exactly. The exact same.
It is fascinating.
Yeah.
Fascinating. So what is a future application of this type of technology?
We're looking at the transducer system, of course, and any kind of mesh network where you have all these different nodes. Say you have a battlefield, and you have tanks. Tomorrow we have drones. We have swarms of drones flying. How do you identify one drone from the other when they're communicating all over the place? Then they have so much intersignal interference. That's one place. So any place where you have these distributed, large-scale wireless kinds of communication networks would be very ideal applications of this technology. And these are coming up. These are the future.
Yeah, these big drone systems. You see these big display things. You see them 4th of July now. They're for entertainment, and also for battle and for very practical applications too.
Yes.
So you can more easily identify each of them and control them without interfering signals.
Exactly. You can individually control each of them at will.
Right. Any type of vehicle, couldn't you?
Any
kind of. I mean, controls of vehicles are getting even more spread. Your own cars, self-propelled vehicles, autonomous vehicles. I mean to say.
Yeah. Another application we were discussing was the smart connected vehicle of tomorrow. We've discussed there's been a lot of work where these vehicles have been hacked. A few years ago, these researchers, they actually took control of a vehicle on the freeway and steered it off the freeway remotely into a ditch and over there. So right from your wireless tire pressure monitoring system. Imagine using encrypted waveforms over there so that nobody can read those signals. Or even your CAN bus, you send encrypted signals all around the CAN bus, because um, even over there, encryption can be important
Hmm. Within the same vehicle, you mean, right?
within the same vehicle.
From point to point within the vehicle, those could still get hacked, couldn't they?
They could, and what could happen is that you can have somebody with a sensor reading your signals wirelessly, because as your signals travel through your car, through the electrical bus, each one of those wires radiates. It's a mini antenna. So it's with somebody with a wireless sniffer may be able to actually snoop out those signals and kind of listen to what your car is doing.
And possibly control it.
Possibly control it. If they're able to hack,
Frightening.
yes, if they're able to hack through the Wi-Fi and you have a connected car, if they're able to identify your car and hack into the Wi-Fi, they can control your car. They take control. They take control of the ECU completely. They can control the throttle, the brakes, the lights, and now since they have electric steering, they may even be able to control the electric steering, especially with all these autopilots and things like that.
Right. I recently bought a vehicle with autopilot. It totally
Yes.
takes control.
Yeah.
And it's not unforeseen that some hacker could get in there and take control
Completely
away from
Yeah.
you.
Yeah.
Well, fascinating. So what other projects are you working on, Ash? You're a brilliant technologist and an entrepreneur, and you're full of ideas. What does your future look like?
Well, I'm also, one of the good things of working in technology is you get to meet so many other brilliant people as well. One of the people I'm working with is Alistair Black, brilliant inventor. We've collaborated together. It's been such an amazing experience. He's, as a person, he's amazing, and he is just full of so many ideas. So right now, what we're working on, we have a patent on communication security. This is more for the internet.
Got it.
And this is a way to provide isolation between two computers. So you have one computer on one side that you want to keep isolated, and you have another computer that's possibly connected to the internet that can be hacked and is exposed to all kinds of potential bad things. So you want to create that isolation. So what we're working on right now is a circuit board that provides that kind of isolation. Normally, you buy what we call a data diode. So if you think about a data diode, you have a source to sink, and it allows data to flow only in one direction. Those are like $10,000, $20,000, $30,000. But our question is, can we bring this kind of technology to the common people? You know, you're traveling, I'm traveling, we have our laptop, and we're connecting to this public Wi-Fi, and who knows what bad agents or bad actors are out there.
Sure.
So is there something we can plug into our system that will provide us with that security and kind of isolate us while still giving us the access?
So how does that work? Is it a type of air gap technology between the two?
It is a kind of air gap technology, but we've implemented it in a slightly different way. We don't implement a physical air gap, we implement a virtual kind of air gap.
How does that work?
So we're using an FPGA, and then we're using the characteristics of the FPGA to implement that kind of isolation. So the FPGA cannot be hacked from a distance. If you want to reprogram it, you need physical control of the device. You need to plug in and reprogram the FPGA. So if you can put in your isolation parameters onto your FPGA, there's very little chance or no chance that the FPGA can be hacked and manipulated.
It sounds hack proof.
Yes,
right?
yes.
Without physically getting into contact with the device.
That's the idea. So without getting physical possession of the device, you're not able to manipulate a very critical component of the system.
Wow, those applications are, I mean, they're almost endless. Give us a few examples.
So again, it's the isolation between your computer when you're traveling, for example.
Right.
One of the things we'd like to develop is like our secure voice communication. You can pipe voice through the system in an encrypted manner and not worry about it being hacked or tampered with. You can do the same for video calls.
So it's an advanced way to encrypt video and audio calls?
It's so the encryption will be done on the laptop itself.
Right.
The data diode or our device will provide the channel for it to be transmitted. It's a hardware device. So it'll provide a channel for it to be transmitted and received with less of a chance of being compromised.
Fascinating. Yeah, I mean, it's a big concern of certainly
Yes.
in wartime around governments.
Yes.
But also everyday communications. With
Yes,
AI,
exactly.
the hacking it's become a superpower, right? It's
Yes,
it's more
absolutely.
advanced than it ever has been.
Absolutely.
And how is it fallible by AI?
That's a good
It's an
question.
open
And
question, right? It sounds like the same principles apply.
the same principles would apply if it is an FPGA-based system, and if
Sure.
the critical functionality is on the FPGA, that would still make it difficult for AI to get into it.
Right, because AI has no physical advantage. It's really just compute power, right?
Exactly. So that's where we're going, and we're hoping to price it competitively so that we allow more mainstream users rather than specialized. So you have a DoD project, you want your data diode, you spend $10,000, $20,000, $30,000, you get it, it's application specific, you need it.
Right.
But how about if we take this kind of technology and make it available for $1,000, which
Everyday
guarantees
use.
some kind of security, everyday use. It guarantees some kind of security for more mainstream users. We do see a very lucrative market there.
Fascinating. Well, Ash, thanks for being a guest on this show.
Of course.
Good to talk to you. Any last words? How about some advice to budding entrepreneurs and technologists who are looking at a uncertain future like we all do when we're young?
Yes. Well, just a couple of words. One, don't stop thinking. Always keep thinking. Don't let that spark ever die. And it may get dark. It may get things may appear gloomy, but never give up hope. Just keep going, even if it means you put it on a back burner and work on it when you can. If you have that spark, if you have your idea, if you believe in it, just keep going.
Don't give up on your dreams.
Do not give up on your dreams.
Ash, great words of advice. Thanks again for being a guest, and I hope to see you again on Innovator Cafe.
Absolutely. Thank you for having me. It's been awesome.
Excellent.
All right.
You've been tuning into Innovator Cafe, the entrepreneur go-to, with your host, attorney Dave Stevens. You can find more episodes on all the major platforms, including YouTube, LinkedIn, Facebook, Apple Podcasts, Spotify, and the website StevensLawGroup.com. Thank you for your positive reviews, comments, questions, and for sharing this show with others.